here. Oops, that's not what I meant to do. Why? I was like, why does that look so ridiculous? Because the camera is all like this. Okay. Stuff here. Cool. Right there. Right, whose class are you? Whose class are you? And what are you all up to in class?
We just got to 2.5.
Okay. All right.
But it's not going to be a lot of our.
Sure. Okay.
We just let's make sure.
Okay.
And a little bit behind.
That's, I mean, that's maybe like, I would like, I mean, so, I mean, because what, we're like, this is week 3, right? There's, I mean, I don't know, there's chapter 3, chapter 4. That's kind of all there is after. I mean, there's not a whole, like, it doesn't feel to me like there's a ton to get through at this point, at least from where you're at. So I wouldn't say, I would say you're not behind. I say other classes might be too far ahead. Right, yeah. Mm-hmm. Yeah. Okay, let's see. So to that end, I guess, yeah. So again, if there are other things you want to see, let me know. I'm happy to like do things, but let's go ahead and do a delta epsilon proof. Now I should ask, in this class, how many of you have been having to do the delta epsilon proofs where you like, you pick delta to be the minimum of typically 1 and some other thing? Raise your hand if that applies to you. Okay. How many of you have been doing the other way where you have to like set the two things equal to the other 2 things and find delta to be the smaller of the 2 things? Okay, cool. So let's kind of walk through another delta epsilon proof and kind of see, and we can probably do it both ways. So yeah, I'll just wing it. I can come up with an example. Yeah, for sure. Right, exactly. Yeah. So yeah, the problem is at least like on an exam, they're certainly kind of expecting to see one thing versus another thing. So not that it's wrong to do it another way, just that if your teacher has taught it a specific way, they're probably expecting to see it that way. Not that you couldn't do it the other way, it's just they might mark it down and you might have to go argue with them later about how, well, this is the right way of doing it as well, just a different way. So just something to be aware of. It depends. Typically, no. Sometimes, depending on the professor, sometimes they grade some of the tests or a question on the test. I certainly, back when I was a grad student, was a TA for a professor who, like, we all sat down and graded the exams together, and he was grading one of the questions, and I was grading one of the, like, so it depends on the professor. Mm-hmm. Sure. Okay. Sure. Well, again, right, you can always make your case later on. So let's look at an example. Let's look at maybe 2 examples. So let's say we want to prove limit x approaches 5. Let's do an easy one first. Let's go back to the good old days of easy delta epsilon proofs. The limit as x approaches 5, 3x minus 8 equals 7. You look at this problem, you recognize it's linear, you already know what delta should be. Delta is going to be epsilon divided by how, show me on your fingers, epsilon divided by how much? Yeah. Just hold on. Yeah. Okay. Yeah. So we know for linear ones, delta always ends up being epsilon divided by the absolute value of the slope. So here we know already, or at least we might know, the delta is going to equal epsilon over 3. Cool. We should still show the work, right? Just saying that is probably not going to be sufficient for someone's grading the exam. So we're going to, let me make sure. Yeah, okay, we're good. Right? Yeah, I'm sharing my screen. We are going to, I want to make sure I notice if anyone comes in. There's no one on Zoom yet, but there could be later, so I don't want to miss them. All right. Sorry, one second. Cool. So here's the work I'm going to do. I'm going to start with, and this is kind of, again, this is kind of my side work. So I'm going to start with the absolute value of f of x minus L less than epsilon, aka the absolute value of 3x minus 8 minus 7 less than epsilon. I'm going to work on that until I get to x minus 5. I'm always trying to get down to x minus whatever x is approaching. This is pretty straightforward. We have 3x minus 15 less than epsilon. We have the absolute value of, or 3 times the absolute value of x minus 5 less than epsilon. So we get absolute value of x minus 5 less than epsilon over 3. And that is our choice for delta. To me, this is kind of like the not actual proof writing part. This is kind of like the background behind the writing of it. And then we're going to write the proof. So now our proof. So we're going to let epsilon be greater than 0. And again, right, there are different styles of writing this proof. This is the way I particularly like to do it. I like to tell them what we're going to tell them. So we want to find delta greater than 0, such that if 0 is less than the absolute value of x minus 5 is less than delta, then the absolute value of our function minus its limit is less than epsilon. That's what we are trying to prove. That we can find such a delta so that whenever x is within delta of 5, f of x is within epsilon of 7. That's the whole story. And again, just as a reminder, all this part here says is x is close to 5. Right? That's really all that says. All this part here says is that f of x is close to 7. We're just talking about closeness. Okay. So then we do it. So we're going to pick or choose delta equal to epsilon over 3. Because we already did the work. You might reference the work above, maybe like because of that. And then we're going to say, and here's where people are definitely like, I'm going to do all the steps, or I'm going to do none of the steps. So some people say, so I'm going to show you none of the steps and all steps. So then people say, then the absolute value of x minus 5 less than epsilon over 5, bigger than 0, implies, and some people just jump straight to the end. Like, it gives me exactly what I want. It gives me that the absolute value of f of x minus the limit is less than epsilon. That's the total sum of what some people like to write. I'm gonna fill that in a second, but I'm just gonna show you that that could be enough. We know that because of all this work we did up here, right? This is less than that, which is the same as that, which is the same as that, which is the same as that. So saying that's true, you can certainly go back to get to that. And then I like to say at the end, thus we have proven, or we have that the limit x approaches 5 of 3x minus 8 equals 7. Period, box, building. Right, that's the universal symbol for we proved the thing we wanted to prove. So here's the stuff that you might not necessarily need to write, but that I usually like to write. I like to, I wrote a 5 there. It should be a 3. Sorry about that. My 5s and my 3s look similar sometimes. So if I was showing all the work, I'd be like, okay, this gives me this. 3 times the absolute value of x minus 5 is less than epsilon. And then that gives me the absolute value of 3x minus 15 less than epsilon. And then that gives me the absolute value of 3x minus 8 minus 7. So I don't necessarily think you need to show those intermediate steps, but you certainly can. It's not all, but a decent amount of this is about just kind of conforming to the style that your instructor has kind of imparted to you. Question or observation? Okay, you sure? Yeah. Okay, you might have something good to say that everyone else wants to hear. Okay. All right, I just other questions about this before we do a more complicated one. Uh-huh. Okay, we can do that. So we want to prove the limit as x approaches a of the square root of x is equal to the square root of a. And here's what so honestly, here's what I might do if I was like having a hard time thinking about how this was going to work because I don't have a real number. If I really couldn't like fathom this for myself, what I would probably do is actually pick a number for a that's nice, write the proof out that way, and then replace the number with a. Does that kind of make sense? So I might instead first say, well, okay, I know I want to do this, but I'm having trouble visualizing how it's going to work. So I'm going to instead prove the limit as x approaches, I don't know, let's pick 9 of the square root of x equals 3. We're going to do that first, and then we're going to kind of fill in the spots with the things we actually need. So, okay, and I'm going to do this, I'll do it the book way, I guess. So we know that we need the following. We need both the absolute value of x minus 3 less than delta. And we also need the absolute value of the square root of x minus, sorry, oh, that shouldn't be x minus 3, that should be x minus 9, sorry. And we need that square root of x minus 3 to be less than epsilon. Okay. Or just to kind of think about what's going on here, right? We know that when we do this, that's actually going to be our a, and that's actually going to be our square root of a. I'm already kind of thinking ahead to what I'm actually going to do. This is more work than you would need to do, right? But again, I'm trying to make it make sense to myself. So then we do the thing where we kind of isolate x in both instances here. So here I'm going to have x minus 9 less than delta, bigger than negative delta, except right, they're different deltas typically. So really this is going to be less than or bigger than negative delta 1, smaller than delta 2. Right? When you're doing these nonlinear ones, your deltas are never the same, or almost never the same. I guess there could be the same, but probably not. And over here, the epsilons are the same. So we have the square root of x minus 3 less than epsilon, bigger than negative epsilon. I feel like 3 just shouldn't be allowed to be used in these because 3 and epsilon is so easy to change. Okay, so over here, we've got x less than 9 plus delta 2, bigger than 9 minus delta 1. Over here, we've got the square root of x less than 3 plus epsilon, square root of x bigger than 3 minus epsilon, and we're going to square both sides. So 3 minus epsilon squared is less than x is less than 3 plus epsilon squared. And then we set these things equal to each other. So we're going to set this equal to that and this equal to that. And we're going to solve for delta. We're going to try and find which delta is smaller. Now, here's the great thing about some of these, especially one like this. So just as a kind of, where's my paper? It's all right here. So just as something worth noting, for functions that are easy to graph, especially like ones like the square root of x or 1 over x things that you kind of know the behavior on one side versus the other. If you're graphing, I'm going to make it real exaggerated here, the square root of x, it is steeper in the beginning and less steep as you move forward to the right. So if I pick a point here and I go the same distance, say above and below, the below distance is going to have a relatively small delta, whereas the above distance is going to really kind of go way out. So just looking at this picture here, I think it can be relatively clear to say that, well, this is obviously going to be the smaller delta because it corresponds to the portion of the graph that is steeper. If you have the steeper portion of the graph, you get the same amount of y change with a less amount of x change. Whereas if you have the less steep part of the graph, you have the same amount of y change for more x change. So you can kind of already know what delta we should be picking here. I should be ending up picking the delta that's to the left, which is going to, whoops, where'd you go, paper? Losing stuff a little. Where did you go? I really like, did I put all my papers on my paper? Sorry. I can't keep track of anything here. It's gone forever. I've lost it. Like really, what's that? I don't know where it went. I don't know where it went. Like it's really like, oh, there it is. Okay, it's hidden in the middle of the stack. Okay, great. So looking at that picture, I am pretty confident that it's going to be right. Solving this equal to that. Sorry, you can't do that. Solving this equal to that is going to give me the delta I need. I should probably still do both, but maybe not. Depending. Like I would say, if I was in a time-based situation, I would definitely kind of maybe not do all the work. I would do this. I'd say, okay, well, I'm going to set that equal to that. So 9 minus delta 1 equals 3 minus epsilon squared. Take the square root of both sides. Oh, I'm solving for delta, not epsilon. So I've got 9 minus 3 minus epsilon squared equal to positive delta 1. And then you can simplify this. That's going to be 9 minus 6 epsilon plus epsilon squared. I don't know if you really need to solve for this, but you can. And we get delta 1 equal to 9 minus 9 is 0. So I get 6 epsilon minus epsilon squared. If we did look at the other one just to kind of be complete about it, and I should have used the same color, I used the opposite color. Oh well, that's what that's giving me. And then over here, I set 9 plus delta 2 equal to 3 plus epsilon squared. Solving for delta 2, I get delta 2 equal to 9 plus 6 epsilon plus epsilon squared minus 9. So I get 6 epsilon plus epsilon squared. And the nice thing about this one is it's actually very obvious which one is smaller. 6 epsilon minus epsilon squared is for sure smaller than 6 epsilon plus epsilon, which is great. So now we can kind of see, so just to kind of finish off this proof with these numbers, to kind of say how I would do it, here's what I would do. So I would say, if I was trying to actually prove this, okay, come on, paper. Always a struggle. So if I was trying to prove that the limit x approaches the square root of 9, sorry, as x approaches the square root of 9, terrible thing. Gosh, looking at 12 different things at once here. Let's try that again. I was trying to prove the limit as x approaches 9 of the square root of x equals 3. I would start with the same sort of preamble. I'd be okay, let epsilon be greater than 0. We want a delta greater than 0 such that if 0 less than the absolute value of x minus 9 less than delta, then the absolute value of the square root of x minus 3 is less than epsilon. And then we're just going to say what delta should be. So we're going to pick delta equal to 6 epsilon minus epsilon squared. And then here's what I would say. I definitely am not going to repeat this work again. So I would probably have written this out in a way so that the person grading it could see it. And then I would say, then by the work above, we see that the absolute value of x minus 9 less than delta certainly gives us that the absolute value of the square root of x minus 3 must be less than epsilon. Proved. Thus, the limit is what it is. So that's how I would write a proof like this. I would do the actual algebraic manipulation all up here, and then I would write my fairly nice kind of clean words down there. So now, question? I was afraid it's almost that. There's no good formula for writing. So actually that's not entirely true. If you look on, in fact, let me show you all. One sec. That's not what I want to click on. I do have a template on Canvas. It's more of a template for the linear proof though, not for the nonlinear proof. It doesn't mean you couldn't modify it. log in because come on, let me in. Modules. Okay, let's take a look here. So if we scroll down here. Yeah. So if you scroll down in the modules in our co-class canvas, there is a delta epsilon proof template, which I think has some blanks to fill in. I don't know. Right. Yeah. So this is kind of, here's a blank kind of one where you are supposed to kind of fill in the blanks. But it is kind of the template that I use, right? I'm always doing this thing where I say, let epsilon be greater than 0. We want to show that there can be a delta. If x minus a is less than delta, then f of x minus the limit is less than epsilon. So find the delta, and that's where you do all the work on the side. In a linear case, so here we all might know that delta should equal to epsilon divided by how much? 2, right? The coefficient of x. Linear, you always get to just say, oh, delta is going to be epsilon divided by the absolute value of the coefficient of x, right? You don't want to divide it by -2 if it's a negative. And then we kind of write the results. Then x minus 6 less than epsilon over 2 gives us all the intermediate steps until we get the thing we want. So right here's x minus your whatever x approaching less than your delta, and eventually it's going to lead you to f of x minus your limit less than your epsilon. So this is the template I use. The only difference between, I guess you could still use this template for a nonlinear one. The only difference is that you can't really, over here. Sorry, there's something open that's weird. You can't really do this set of implications here. I would be instead saying then x minus a less than delta gives us automatically f of x minus l less than epsilon. I'm not going to write all the intermediate steps because they're a giant pain to write. And they're not really backtrackable, is what I would say. Okay. So, yeah.
Is it bad to write like the minimum of each delta? Because I noticed that people go back and forth between like figuring out which one is the smaller one and just writing the minimum.
In this case, I would say it is very straightforward to see which one's the smaller one. Now, what I don't think you're saying is we're not talking about the thing where you say delta could equal 1 or this other value, right? Okay. Because in those you do need to specifically say the minimum of 1 and whatever. But we're not doing that. It should technically be fine to say delta is the minimum of those two deltas. Like that's not a wrong thing. I like seeing what it is, but that doesn't mean and there are definitely other problems where it's harder to see, like where you'd have to actually plug in some values for epsilon. So I think in the time crunch situation, it's definitely like, yeah, say delta is the minimum of the two deltas. That's probably a good thing to do. If you have all the time in the world, though, it's usually, I would want my students to find which one is the small one. Okay. Yeah. But technically, it would be correct to say delta is the minimum of these two values. That'd be totally fine. I guess the idea is sometimes it's really easy to see what the minimum is, sometimes it's not. Let's go back to the question you asked, which is doing this with A instead of 9. Well, let's take a look. I'm not sure. So let's go ahead. So basically what I'm gonna do is I'm gonna walk through the same work, except I'm just gonna throw in A and square root of A instead of 9 and 3. So I'm really, because I need to see how it's gonna go. So let's copy this down. So really, I'm just kind of writing the same work. So I need the following. I need both the absolute value of x minus a less than delta, which if we work that out, that's x minus a less than delta 2, bigger than negative delta 1, x between a plus delta 2, bigger than a minus delta 1, and also the absolute value of the square root of x minus the square root of a less than epsilon. So isolating x, square root of x minus square root of a less than epsilon, bigger than negative epsilon, square root of x less than, I think the epsilon's first, the a's first, it doesn't really matter, I guess. square root of a plus epsilon bigger than square root of a minus epsilon, and then square both sides. So that you have square root of a minus epsilon squared less than x less than square root of a plus epsilon squared. And then we're going to do the same thing. We're going to set that equal to that and that equal to that. So doing that, so we know that the delta, at least I'm fairly certain, right? My graph didn't change. It doesn't matter if this is 9 or 16 or 36 or whatever. No matter what point I'm picking here, it's still the truth that the left side is steeper and the right side is not as steep. So it should still be that delta 1 is the smaller value. Which is the nice thing about the square root function. Or any function that's always increasing or vice versa, always decreasing. Kind of works out nicely. No, I shouldn't say decrease. I should say concave down. That's actually what I mean. Anyway, so setting these two equal to each other, I have a minus delta 1 equal to the square root of a minus epsilon squared. And solving for delta 1, I have a minus delta 1 equal to, I'm going to multiply this out and get a minus 2 epsilon root a plus epsilon squared. Those cancel. Delta 1 equals positive 2 epsilon root a minus epsilon squared. Setting those two equal to each other. Now I know this is the one though. That's the one for sure. Like I'm 100% certain. But let's look at the other one. Multiply, setting that equal to that. We've got a plus delta 2 equal to the square root of a plus epsilon squared. So a plus delta 2 equals a plus 2 epsilon root a plus epsilon squared. The a's cancel. And yeah, that is definitely a bigger value. So that's the one we want. Yeah. Sure. So let's take a look. If we factor out an epsilon, I've got 2 root a minus epsilon. So I suppose it is possible that we could pick an epsilon. Yeah, I'm curious. Let's see. Let's look back at the other one. So looking back here, I suppose that's also true, right? I could pick an epsilon where this delta was negative. It'd have to be fairly big though, right? So here, if I say that this is the smaller one, that's equal to epsilon times 6 minus epsilon, right? So if I pick epsilon bigger than 6, I'm gonna have a problem. I would say greater than 2a. Yeah, 2 root of a. Yeah. Sure, you're right. I don't know. That's a good question. I'm not sure about the answer to that. I would probably, if I was in a test situation, I would probably just ignore it. Honestly, like I would say, like, well, not exactly sure, but I know that this is the smaller one. Or I would maybe do the thing that she said to do, which is to say pick delta to be the minimum of these two. Right, the other one's always positive. Yeah. Yeah. Yeah, I guess that's what I would do. Well, yeah, because our assumption is the delta is positive. So. Okay. For those of you coming in Zoom, let me give you all the attendance form. All right, so I think not that you could ever really talk about delta epsilon proofs enough, right? You could talk about it till time and probably still be like, well, what's going on here exactly? But let's move on from the delta epsilon proofs to talking about continuity. I think continuity is something that we could certainly spend more time on. And let's see. Come on, papers. Get more. Okay. So yeah, let's look at some continuity. And I think so. Someone said something about trig continuity. So let's see if this is kind of what you're looking for. And if it's not, we can certainly do more. So let's say we have the following function. F of x equal to -4 cosine of x plus 1 times pi when x is less than 2. 17 when x is equal to 2. and the cube root of x plus 6 plus x squared minus 2 when x is greater than 2. And so there's a couple ways you could phrase this question. I could ask you, where is this function continuous? Or I could specifically say, is this function continuous at 2? Because this function is definitely continuous everywhere else. It's definitely continuous if x is less than 2, because cosine of x plus 1 pi times -4 is a continuous function everywhere it's defined. Similarly, it's definitely continuous everywhere greater than 2, because the cube root of x plus 6 is a continuous function everywhere. It's defined, which is defined everywhere. So the only place in question is this continuous at 2? Is this continuous at x equal to 2? And to answer that question, yeah. No, you're good. No, it doesn't. Yeah, you can say something is a minimum of 1, 3, or the minimum of 3, 1. You're still getting 1 because it's always the minimum of just whatever. So here we have 3 things. So if you see a continuity question, you should always think there are 3 things I have to do. I have to, 1, make sure that f of 2 exists. 2, make sure the limit as x approaches 2 of f of x exists. And 3, make sure that they're equal to each other. Those are the 3 things we need to check for continuity. I will also say you don't have to check all of them if one of them fails. Right? Once something fails, you're done. It's not continuous. Excuse me. So f of 2, easy. 17. Right? They told us that if you plug in 2 for x, you get 17 for y. Very straightforward. The next part's not quite so easy. So the next part, we have to do the left and the right hand limits. And that's very typical for these piecewise functions where you have something on one side of 2 and something on the other side of 2. So let's look at the left. Let's look at the right hand limit first. So the right hand limit in my mind is slightly easier to calculate. So limit as x approaches 2 from the right. We are using the piece where x is larger than 2. So we're using all of this here. So it's going to be limit as x approaches 2 from the right of the cube root of x plus 6 plus x squared minus 2. Most of these problems are designed so that evaluating the limits is as easy as plugging it in. Occasionally not, sometimes it's a little harder, but here we can just plug in 2 and get the cube root of 8 plus 4 minus 2, which is 2 plus 4 minus 2, which is 4. Now, at this point, we can answer the question kind of. I can say 100% with 100% confidence, this function is not continuous at 2. Sometimes people want you to say why it's not continuous, meaning what failed. And at this point, I can't actually say it. I can't say that it's not continuous because the limit doesn't exist, because I haven't checked the other side of the limit, because maybe the limit does exist. If the limit does exist, it would have to be 4, which would then mean part 3 would fail. So typically, I like to be thorough and check and actually say why the thing is discontinuous. So let's go ahead and check the other side of the two-sided limit. So the limit as x approaches 2 from the left is going to utilize this piece right here. So that's going to be -4 times cosine of x plus 1 times pi. And if I plug in 2 there, let's see what I get. I get -4 times 2 plus 1 is 3. So cosine of 3 pi. And what's cosine of 3 pi? Let me ask you all a different question. What would cosine of 3 pi need to be for the function, for the limit to exist? Same answer. It would need to be -1 so that we got -4 times -1 equal to +4. So I'm looking at that thinking, well, it's probably going to be -1. And it is. Cosine of 3 pi, right? You start over here, you go all the way around, and then you go halfway around again. You're over here at -1, which is going to give you the -1. So that is equal to -4 times -1, which is 4. So the limit does exist. Limit as x approaches 2 of f of x is certainly equal to +4. So check, but then part 3 fails. Right? The limit is not equal to the function value. So we can say that f of 2, which is equal to 17, is not equal to 4, which is what the limit is equal to. And that means that the function is not continuous at 2. Yeah. Well, what do you mean exactly? Sure. Upside down A. I don't think there's a really good like very small like continuity is just a thing we talk about. Like there isn't a good symbol for it. Yeah. Sometimes you actually have to write words and not just mathematical symbols. So is this kind of whoever asked about the trig thing? Is this kind of what you meant as far as the trig goes, or is there something else you were kind of thinking about? Is that okay? Let's look at another example because I do like let's look at one more example like this. And I'll try not to make it too similar to the one I did before. I do like so let's say I want to find I have I had a good one. Is that really good? No, we're not there yet. That'll be for next time. I had a good one, but it's more about something else. So let's say we have a function f of x equal to, sure, 3x minus 1 when x is less than or equal to 2, and x squared plus 2 when x is bigger than 2 and less than let's say 5. And then let's say we have I'm gonna make this, that's gonna be good. Sorry, once I have to think for a second here. All right, we're gonna make this a little tricky. We're gonna say we have sine cubed of 3x over x cubed. No, darn it. Sorry. I always do this thing where I think it's gonna be cool. Trying to make it cool. But I forget one important fact, which is that I'm not at 0, which is terrible. Fine, we'll just do it anyway. We'll do another one after this. It'll be cool, I promise. Not that it has to be, like, I'm sure this is helpful. I just thought it was like, oh, well, it's not as interesting as it could be. Fine. So let's talk about continuity. Where do you think we're interested in continuity at? Where 2 and 5. There might be one other place you might think about continuity here. Like if someone said, where is this function continuous? You might say, well, I'm going to look at 2, I'm going to look at 5, and then I might at least think for a second about 0. Now, I don't really have to, because although this function, sine cubed of 3x over x cubed, is certainly undefined at 0, its domain does not include 0, so we're safe. We don't have to worry about 0 here. So 0 is not an issue. It's not a point of concern. Typically, when people ask these questions, they'll just ask you, like, is it continuous at 2? Is it continuous at 5? But sometimes people are a little more general and they say, where is it continuous? Yeah, I mean. Because, so it's totally true that this piece here is undefined at 0. But this piece is only defined to be, or this function is only defined to be this piece when x is equal to 5, or greater than or equal to 5. So if I was worried about 0, here's the work I would do for 0. So let's pretend like we needed to look at continuity at 0 for a second. So first things first, is it defined at 0? Let's see, f of 0 is, well, I'm going to use the piece where x is equal to 0, which is this top piece here. And when I plug in 0, I get 3 times 0 minus 1, which is negative 1. Right? This is not coming into play. And then the second part, does the limit exist? The limit as x approaches 0 of f of x. Well, on the right of 0 and on the left of 0, it's still this same function here, 3x minus 1. So I'm just going to use the limit as x goes to 0 of 3x minus 1, which is going to be negative 1. And then part 3, they're equal to each other. So it's totally continuous at 0 because we meet all 3 criteria. The function exists there, the limit exists there, and they are equal to each other. And the next problem I make up where I'm not going to make this dumb mistake I've made twice, I'll have a cooler thing out, but fine. Okay, so x equals 2. All right, so most of these problems, you're usually not going to fail on the first thing. Meaning most of the time, if someone's giving you a thing to find out if it's continuous, it's usually going to be defined at the point you're looking at. It kind of is lame if it's not, right? You're like, oh, it doesn't exist. Great, done, move on. But that is something still to look for, right? Because maybe someone's going to throw you a curveball. Like, oh, yeah, it's actually not defined there. Here we have f of 2 equal to 3 times 2 minus 1, which is 5. Limit part. So that's part 1. Here's part 2. Limit as x approaches 2 from the left is going to use the part where x is less or left of 2. And I'm just going to plug in 2 and get 6 minus 1, which is 5. On the other side, the limit as x approaches 2 from the right, I'm going to be using this piece, the x squared plus 2 piece. And that's going to end up equaling 4 plus 2, which is 6. And so then we stop. Right? We say, oh, the function is definitely not continuous there because 5 doesn't equal 6, because the limit doesn't exist. So notably, though, this function is discontinuous at 2 for a different reason than the other one. The other one was discontinuous at 2 because the limit existed and the function existed, but they weren't equal to each other. Here, the function is not continuous at 2 because the limit doesn't even exist. So the limit as x approaches 2 of f of x does not exist. So f of x is not continuous at 2. All right, let's look at the other point. We get 5, which I'm almost 100% sure is not going to be continuous. I'm very sure. So f of 5, f of 5, all right, good times. F of 5 is going to be sine cubed of 3 times 5 over 5 cubed. That is a hideous number if I ever saw one. Here's what I would encourage you to know about this terrible number. It is less than 1 over 125. Because sine is less than or equal to 1, and sine cubed is less than or equal to 1. So sine of this 15 cubit is less than 1, and then divided by 125 is less than 125. So I know that might not seem like a big deal, but it is, because then if we try and find the limit from the left and the right, the limit as x approaches 5 from the right-hand side of sine cubed of 3x over x cubed is the same thing. It's sine cubed of 15 over 125. Not lovely. Limit from the right, limit from the left. What's the limit from the left going to be? Well, if I plug in 5 there, I'm going to get 27. Are these two equal to each other? For sure not. We know that's not 27 because it's definitely less than 1 over 125. So sometimes you won't know exactly what a thing is, but you'll know it's definitely not equal to the other thing because it just can't be. Okay, so that example was not exactly what I was looking for, but let's go ahead and actually write something that's going to be interesting. Okay, so one more example. Well, maybe not just one, but another example of, is this function continuous here? Because definitely, if you haven't already taken your first midterm, I would imagine, or exam, right? Midterm is probably not the right term. There's probably going to be a question about continuity down there. It's a pretty typical standard first test kind of thing to put on there. Okay, and it's almost often always a piecewise function. So let's look at this thing that I actually want to do here. Let's say we have, sine squared of 3x over 4x squared when x is less than 0. Great, got it right. Let's see. I have to think about what the answer is going to be. Okay, yeah. And then, yeah, that would be interesting. Let's say we have. I have to do that. Okay. So we're just going to have something simple like, x squared plus, x squared plus 9 all over 4 when x is bigger than or equal to 0, less than 5, and then finally 2x cubed. Okay, so aside from 0 and 5, are there any other places where we are concerned about continuity? Is there any other places where we might be dividing by 0, taking the square root of a negative, or taking a logarithm of a negative or 0? No, right? The only place where we might be dividing by 0 is if x is equal to 0. We're already concerned with that spot because of the changing point. So let's look at x equal to 0. And the reason I really asked this question was because I want to show you a thing. So first and foremost, check the first thing. What's f of 0 going to be? So I don't plug it into the top part. I plug it in the middle part because that's where x is equal to 0. Oops. Oh, okay, fine. This is a good question. And I get 0. All right, sorry, I saw a thing, but so plugging in 0 there, we get 9/4. Okay. Whenever you're doing these piecewise function kinds of things, one of the one-sided limits is always going to, well, unless you got the middle, like unless you do like the first one we did, we had the 17 in the middle. Typically, if it's like a two-sided thing, one of the sides is going to be the same value. So here, if I do the limit of x equals to 0 from the right, I'm also going to get 9/4. I'm just using the same piece of the function. So I think it's pretty safe to say that we know that the limit as x approaches 0 from the right, I'm still using this piece, I'm still going to get 9/4. So the question really is, what about the limit as x approaches 0 from the other side? So the limit as x approaches 0 from the left of sine squared of 3x over 4x squared. That's a 0 over 0 type of limit. So we have to do more work than just saying we don't know or something. So this is one of those ones where we're going to use what I like to call the wish method. Now, when I see sine squared of 3x, I'm thinking sine of 3x times sine of 3x. Or sine of 3x quantity. But I really actually want to write it out into many fractions. At least I do when I do it the way I like to do it. So I'm going to write this out as the limit as x approaches 0 from the left of sine of 3x over blank times sine of 3x over blank times blank over 4x squared. And then, of course, what do we wish we had underneath the sine of 3x? A 3x. Which means if we have one below, we have to have one above to compensate. And what do I wish I had beneath that? Sine of 3x. Another 3x. So one below, one above to compensate. Okay, why do we wish there was a 3x there? What's the limit as x goes to 0 of sine of 3x over 3x? 1. So this ends up equaling 1. And now I hesitate to say this because it's really the limit is 1. So it's going to 1. And this is going to 1. And this is 3 times 3 over 4. Because the x's cancel. Which is exactly 9/4. So the limit exists. The limit from the left is 9/4. The limit from the right is 9/4. So we can definitely say that the limit as x approaches 0. Oh, I wrote f, but then I was using g. Sorry. All this f. Apologies. The limit as x approaches 0 f of x is indeed 9/4. Cool. And then finally, since the function value is 9/4 and the limit value is 9/4, we can say that f of x is continuous at x equal to 0 because the function value is equal to the limit value. Nice. All right, let's look at the last one. The last part, x equals 5. So part 1, what's f of 5? Doesn't exist. All right, this function is not defined at 5 because someone forgot to write an equal sign somewhere. But if you saw this on your test, I would not say anything. I would be like, hey, teacher, is this supposed to be a no? You'd be just like, well, f of 5, not defined. So the function is not continuous at 5. That's what I would do because it's an easy answer. You don't have to work that hard for it. Maybe they didn't mean to do that. I definitely wouldn't have meant to. I didn't mean to write this when I wrote it. I meant to define equal to 5 somewhere, but I forgot to. And if I'm grading this later, I'm like, shit, I forgot to write the equals 5. They're right. I'm not gonna like say they're not right because I forgot a thing. So if that happens, I mean, maybe they're doing it on purpose. I doubt it. But if you saw that, I would just take the gift horse you've been given and run with it. Okay. Yeah. Yes, you could certainly say that this function is continuous on its entire domain because the domain does not include 5. Okay, let me ask. Sure. Correct. With the parentheses on the 5s. And then, yeah. Other questions about it? Yeah.
Would sin x over x only be equal to 1 if it's the limit is tending to 0?
Yes, so I would say, and actually that's where I was going to go next. So let's look at some examples. So there's this whole thing about how, yes, and I know we talked about this a little bit before, but it's good to revisit. The limit as x goes to 0 of sine of x over x is equal to not 0, 1. Or as I like to think of more generally, the limit as some stuff goes to 0 of sine of the stuff over the same exact stuff is going to equal 1. So here's an example that doesn't look exactly like what you might think it should look like. For example, the limit as x approaches pi over 2 of sine of x minus pi over 2 over x minus pi over 2. So when I'm looking at a question like this and trying to find the limit, I'm always asking myself 2 questions. Is the thing we're taking sine of and the stuff we're dividing by exactly the same? Yes, the stuff is exactly the same. So these are exactly the same. Great. Question 2, are they both going to 0? Yes, right? I don't care what x is approaching. I care what the stuff is approaching. So my stuff is x minus pi over 2. And since x is approaching pi over 2, we can say that our stuff is approaching 0. So this is totally going to be equal to 1. And if you wanted to rewrite this in a not typical, and definitely more annoying way, but in a more kind of demonstrative way, you could totally write this as the limit as, instead of saying x is approaching pi over 2, you could say that x minus pi over 2 is approaching 0. That's the same thing. If x is getting closer and closer and closer to pi over 2, then x minus pi over 2 is getting closer and closer and closer to 0. Because x is getting closer to pi over 2. And then it really looks like what we want it to look like. You've got sine of some stuff over the exact same stuff, and that stuff is getting closer to 0, so the limit must be 1. Question. You can do a substitution, but it's really not necessary. No one is at least in my opinion, no one's looking for you to do this at all or to do a y substitution. They're really just looking for you to recognize that you've got sine of a thing that's going to 0, the same thing on the bottom is going to 0, and that limit's going to equal 1. Okay. Only for sine, exactly. If someone throws a cosine at you, well, I'm gonna recant that just a tiny bit. I'm gonna take it back just a tiny bit. It is only for sine and for tangent. It works for tangent too. But really it's because tangent has sine in it. So, but I would say if you see it like for cosine, if someone says, what's the limit as x approaches 0 of cosine of x over x? Well, this one's gonna not exist. Because if we look at 0 from the right, you approach 0 from the right-hand side of cosine of x over x. What's cosine of 0? So I've got 1 over a small positive number, and 1 divided by a very, very, very small number is going to be very, very, very large. This is going to blow up to positive infinity. On the other side of 0, the limit as x approaches 0 from the left of cosine of x over x. Cosine of 0 is still 1, but now the bottom is a very, very small negative number. So when you have a positive number divided by a very, very, very small negative number, we get a negative thing overall, but it's a very large negative. So that means overall, since the right-hand side's doing this, and the left-hand side's doing this, the overall limit doesn't exist because they're not going towards the same positive or negative infinite value. That's a different story. Yeah. So if instead, exactly. In fact, that's a very important limit that we're eventually going to use when we talk about the derivative of sine and cosine. That limit shows up quite a bit. So yes, if you want to find the limit as x goes to 0 of 1 minus cosine x over x, well, now you're back in a 0 over 0 situation. So you have to do some work. Now I don't just see sine over cosine. So I don't just see sine x over x. So I actually have to do something. I'm going to multiply by a conjugate. 1 plus cosine x. So your goal when you see these 0 by 0 types of limits that involve like a cosine or a sine is to make it eventually look like you have sine of thing over same thing. That is always kind of the thing we're working towards. So here, if I multiply at the top, I get 1 minus cosine squared x. On the bottom, I have x times 1 plus cosine x. And then we know that 1 minus cosine squared x is equal to, right, if the limit as x goes to 0 of sine squared x over x times 1 plus cosine x. And then we have to do the work of breaking this up into pieces that look like something we know is going to happen with it. So I see on top I have sine x times sine x. On the bottom I have x times 1 plus cosine x. And I would really like to group that sine x over x into one kind of individual piece. So I'm going to rewrite this as the limit as x goes to 0 of sine x over x times the rest, sine x over 1 plus cosine x. Totally valid. Okay, what's the limit as x goes to 0 of sine x over x? What's the limit as x goes to 0 of sine x over 1 plus cosine x? Plug it in. Sine of 0 is 0. Cosine of 0 is 1. 0 over 1 plus 1 is 0 divided by 2, which is 0. So you get 1 times 0, which is 0. But it's totally valid, and the kind of the only thing to do is to pull out the sine x over x and then see what the leftovers is.
So in the sine example, what if the limit of ten?
Totally different question. Yeah. So I'll come back around to that in a minute because I do want to talk about that. But let's do a couple more of these first, and then we'll work back around there. Oh yeah, but someone asked about is it only true for sine, and it's not only true for sine, it's also true for cos or for tangent. So let's look at this. Look at the limit as x goes to 0 of. I would ask this sort of question on a test. The answer is not going to be 7 over 6 because we have a sine squared. I will tell you, just as an aside here, if I asked this question instead, limit as x goes to 0 of sine of 7x over 6x, that limit definitely would be 7 over 6. And the way you would show that work would be to do, again, what I like to refer to as, what do I wish for? I wish I had a sine of 7x divided by the same thing. So I'm going to divide by what I wish was there. But then I'm going to adjust. And then the limit of this part is just equal to 1. So I end up with 1 times 7/6, which is 7/6. For me, these problems are always about making it look like what I want. So here, if I have sine squared of 7x over 6x squared, I'm going to do the same sort of thing, but I have to recognize that I have not just sine of 7x, I have sine of 7x times another sine of 7x. So I'm going to write this as the limit as x goes to 0 of sine of 7x times sine of 7x times something over 6x squared. Essentially rewriting out the same thing in a kind of terrible way, right? No one would ever actually write a fraction like this. But so I can leave myself space to fill in the blanks. I want a 7x down there, one up there to balance out. I want a 7x there, one up there to balance out. And then this is going to end up equaling 1 times 1 times the x's cancel, and you get 7 squared over 6. People like to ask this kind of question after you've learned L'Hopital's rule. Because this question is garbage if you try to use L'Hopital's rule. I mean, you'll get there eventually. But taking the derivative of the top part, the first time is not too terrible. Taking the derivative of the top part the second time is really awful. So sometimes I will just warn you, L'Hopital's rule is eventually in the future. It's a great tool to use some of the time. But it's not always the best tool to use. Evaluating this limit, you would never want to do it using L'Hopital's rule. Even though you could, it would totally work out eventually, but it's much easier to do what we've done here. So just be aware, there are tools you will have later on that might not always be the best tool, even though they seem like they're really good to use. I'm not using the addition rule, I'm using the multiplicative rule. Yeah, so there is a rule that says, right, if you have the limit as x approaches a of f of x times g of x, it is certainly equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x, provided they all exist. I don't think you need to reference it. Now, your teacher might have a different opinion. Then you can't use this. The whole, you can't say the whole thing doesn't exist, but we can't use this method to get there. So let me show you an example of that. Actually, the answer to your question, sir. So let's look at, the limit as x goes to infinity of 1 over x times sine of x. Here, you cannot use this multiplicative rule. You cannot say, it's definitely not true, right? This is not equal to the limit as x approaches infinity of 1 over x times the limit as x approaches infinity of sine of x, because specifically, this limit does not exist. If you take the limit as x goes to infinity of sine, that function just keeps oscillating between 1 and -1. It's not getting close to any one particular value. So you can't use this rule here because it's not applicable. So instead, we do something else. Now, here's what I would say. Oh, I forgot about tangent. We'll get back to tangent. Here's what I would say about limits going to infinity involving sine or cosine. So specifically, limits where x is going to infinity and you have sine or cosine. It's not a hard and fast rule, but it's pretty generally true. If you see something like that, like this example here, your brain wants to think of the squeeze theorem. It's generally a squeeze theorem question because although we don't know what to do with sine, because it's just kind of doing this oscillating thing, we can definitely always say that no matter what's going on with the argument of the sine function, it is always 100% true that sine is between -1 and 1. And it doesn't matter if it's sine of x, sine of 1 over x, or sine of x cubed plus cosine of x minus 2. Doesn't matter what the argument of the sine function is, sine is always between -1 and 1. Now you might multiply by some stuff later and do something else, but at least at this point here, it's between -1 and 1. And then I want to take the limit of sine of x divided by x. So I'm going to divide everything by x. And then we take the limit of the outer parts. So the limit as x goes to infinity of -1 over x is 0. And the limit as x goes to infinity of +1 over x is also 0. So by the squeeze theorem or sandwich theorem, if you like to think about sandwiches, I mean, who doesn't, right? Sandwiches are great. By the squeeze theorem, the limit of the middle part has to be 0. And it works for sine x over x or cosine x over x. I prefer a more complicated version of this question. I'm gonna ask, let's look at what I think could appear on some people's exam. If you've dealt with this kind of thing, I would ask a question like, and have in the past, what's the limit as x goes to infinity of, let's not make it too terrible, James, 2x squared plus 3 cosine of x divided by 5x squared plus 3x plus 1. You might already have a very good idea of what the answer is going to be. Let me ask you a slightly different question. If instead you were being asked the limit as x goes to infinity of 2x squared plus 3x plus 6 over 5x squared plus 3x plus 1, what fraction would you know that your limit is supposed to be equal to? Right, it's going to be 2/5. Because when you have limits to infinity of rational functions, the answer is always the quotient of the leading coefficients, if the degrees are the same. I should have said that. If the degrees are the same, the limits of the quotient of the leading coefficients. We kind of have that, except technically this is not a rational function. Because a rational function is specifically a polynomial divided by another polynomial. And the top part's not a polynomial. There's a trig function there. So what do we do? Well, it depends on, I don't know, it depends. There's two ways to go about this. One way is to just start off like we usually would, which is divide everything by what? Divide everything by x squared. So I'm going to say this is equal to the limit as x goes to infinity of 2x squared divided by x squared plus 3 cosine x. I don't think you need to write this step. I think you should skip this step and go to the simplified step. But it's good to show your work also. So dividing everything by x squared and then simplifying, we have the limit as x goes to infinity of 2 plus 3 cosine x over x squared over 5 plus 3 over x plus 1 over x squared. And then here's how people usually do this. They say, oh, that's going to equal 2 plus 0 over 5 plus 0 plus 0, which is 2/5. But then they specifically justify this. They say, because 3 cosine x over x squared is less than or equal to a thing and bigger than or equal to a thing. Specifically, cosine x is between 1 and -1. So 3 cosine x is between 3 and -3. So 3 cosine x over x squared is between 3 over x squared and -3 over x squared. And then they use the squeeze theorem there. So we say that, and then we say, oh yeah, the limit as x goes to infinity of 3 over x squared is 0, and the limit as x goes to negative infinity of -3 over x squared is 0. But there is typically an expectation that if you have this kind of limit where that's showing up, you somehow reference the squeeze theorem about why that limit is equal to 0. Oh, I didn't mean to. Sorry, because I was looking at the -3 and my brain saw a negative sign. Because my brain makes mistakes. That's why. Other comments about this? Yeah. Yeah, of course. Okay. All right. That's probably there's another way of approaching that second problem, but I think the way I showed you is the better way. I will just mention that some people like to start off with the inequality. So some people do this other thing where they start off with this and then they try and make this look like that. It's fine. That's the way I actually tend to prefer to do it. But I feel like students in the past have been like, it's not the easiest way. So you could totally do this, just in case you were looking for a different flavor, and then try to make your inequality look like this whole thing there. So multiply everything by 3, and then add 2x squared to everything. And then divide everything by the denominator. And then you can say, oh, the limit of this is going to be 2/5. The limit of that is also going to be 2/5. So by the squeeze theorem, the middle part, oh, sorry, the middle part is going to have a limit of 2/5 as well. It's the same idea, just a slightly different way of getting there. Either way is totally fine. Okay. There was one other thing I wanted to say about this sign going to 0 kind of thing, which was, yeah, tangent, exactly. So tangent works kind of like sine for those kinds of problems, and because really it's sine over cosine. So for example, if I wanted to find the limit as x goes to 0 of tangent of 4x over 7x, you can just say tangent of a thing over the same thing goes to 1 as x goes to 0. But if you're not super comfortable with that, I would recommend breaking it up into sine over cosine. So I would write this as the limit as x goes to 0 of sine of 4x, over cosine of 4x times 1 over 7x, and then rewrite it as the limit as x goes to 0 of sine of 4x over blank times the other stuff, blank over cosine of 4x times 7x. And again, just like before, what do I wish was beneath my sine of 4x? A 4x. And went up there to adjust for it. All right. It is a good idea to cancel those x's, meaning specifically that one there and that one there. I could rewrite this as the limit as x goes to 0 of sine of 4x over 4x times 1 over 7 times cosine of 4x. And then we evaluate. The whole reason we wrote it this way was so that we can say that the limit of this part here, that's going to be just 1. And this part here, if you plug in 0, you get 1 over 7 times cosine of 0. Cosine of 0 is 1. Yeah. Oh, it should. I forgot the 4. I should keep, man, you get old, you start making mistakes. Yeah, it should be 4 sevens, not 1 7. Thank you. I feel like I'm failing you guys. Error. Like that, yeah. All right, so these sign limits where you have limit x goes to 0, sign something over something, they all kind of work this way. I mean, there's a few other types of varieties, but this is mostly it. It also works if you have the reciprocal. Like for example, if you wanted to find the limit as x goes to 0 of 6x over sine of 17x, you can do the same sort of thing. You can write it as the limit as x goes to 0 of 6x over blank times blank over sine of 17x. I suppose I should have written the sine part first, but I didn't. What do I wish was going with the sine of 17x? A 17x. Now, this thing here does not look specifically the same as what we're used to. We're used to sine of a thing over the same thing where the thing's going to 0. But now we have the reciprocal of that. Here is where we actually kind of, kind of explicitly, here's where we're going to kind of explicitly use one of those limit rules. So I'm going to rewrite this in a way that looks more familiar. I'm going to write this as, well, first I'm just going to cancel those x's. So I have the limit as x goes to 0 of 6/17. And then instead of writing this as 17x over sine of 17x, I'm going to write it as 1 over the reciprocal of that. Sine of 17x over 17x. And now I actually am going to use a couple actually limit rules very explicitly. I'm going to say, oh, this constant can come out in front. And we know that the limit of a quotient is the quotient of the limits. So instead of saying I have the limit as x goes to 0 of 1 over all this stuff, I'm going to say I have the limit as x goes to 0 of 1 over the limit as x goes to 0 of sine of 17x over 17x. We don't often explicitly use our limit rules, but this is a good time to do it. What's the limit of 1? 1, right? Limit of a constant, just the constant. And the limit as x goes to 0 of sine of 17x over 17x is going to also be 1 because it's the same sort of deal. So we're getting 6 over 17. So that's how a lot of these sine problems end up going. You're trying to make it look like sine of a thing over the same thing where that thing is going to 0. All right. What else should we, how much time have we got? We still got like a good half hour. What other kinds of things should we talk about? More limit definition of the derivative. Yeah, I feel like that's not going to be super helpful for everyone to see. What else? What kind of, so we talked about continuity a fair bit. I think we could probably leave continuity. We could probably stand to do another intermediate value theorem question. I think that would probably be worthwhile because that usually shows up on people's first exams as well. So let's talk about the intermediate value theorem again. When I had a thing over here. Yeah. Okay. Oh yeah, here's a good one. Here's a couple good ones. So hopefully we can see pretty easily that x squared equal to 2 to the x has solutions that are x equal to 2 and x equal to 4. Because 2 squared equals 2 squared, check, and 4 squared equals 16, which equals 2 to the 4th, check. But now we're going to use the intermediate value theorem to show that there is one more solution. So here's what's kind of tricky about this one. We're going to use it. So the intermediate value theorem shows that an equation has a solution, typically, in some interval. And it shows that there's at least one solution, but it doesn't show that there's necessarily more than that. So the problem we're going to have to overcome here is that we need to show that there's a solution in an interval. But that interval better not include 2 or 4, because then we can just be like, well, the solution that you found, maybe it was 2. So we're going to have to come up with an interval that doesn't include 2 or 4 that has a solution. Okay, so that's kind of the setup. Now, there's an easy way to kind of figure out what it should be, but I'm not going to tell you right away. So first and foremost, when you're trying to do these things, you always want to bring everything to one side and try and make it a problem where you're trying to solve it equal to 0. So instead of saying, I want to find a solution to x squared equal to 2 to the x, I instead want to say, I want to find a solution to x squared minus 2 to the x equal to 0. And I want it to not be in the interval from 2 to 4. Because otherwise it might be 2 or 4. So this is typically where we have the job of finding values of x, where one value gives us a positive output and one value gives us a negative output. Oh, and it's also a good idea to call this thing that's equal to 0. Let's call that f of x. So our job at this point is to find values of x so that f of x is positive and another f of x is negative. And if you're James, you're always going to start by picking what? You're going to pick 0 because it's easy. So we pick 0. F of 0 is equal to 0 squared minus 2 to the 0, which is 1. Now, it probably would feel pretty natural to start picking larger numbers. Like you might pick 1 next. I'm not saying that's a good choice. I'm just saying it might be what you do. Yeah. Yeah. Killing myself over here with making these errors. Yes. So if you picked 1 is going to be, let's make sure here, 1 squared minus 2 to the first is also -1. That's not super helpful. And picking 2, I know it's a solution. I don't want that. I don't want to go further. I don't want to go further to the right. So if I start going further to the right, I'm going to end up including a place where there's a solution. I expect to go the other direction. Now, I should point out, there's a much easier way to determine which way to go is, and that is to kind of make a quick sketch of what the graphs look like. So here's x squared. And here's 2 to the x. And they intersect here at 2 comma whatever. And then they do intersect again later on, right over here, where this one gets super steep and the other one doesn't quite steep. So it looks like I should definitely be looking for a solution over here, right? There is a solution that is a negative value of x that we haven't even considered. So definitely starting at 0 is good, and then going to the left is what we want to do. So let's try x equal to -1. So if I put -1, I'm going to get f of -1 is -1 squared minus 2 to the -1, which is +1 minus 1/2, which is +1/2. Great. I'm happy about that because now I have f of 0 is -1 and f of -1 is +1/2. So from 0 to -1, I've gone from being negative to being positive, which means I had to have crossed 0. Okay. Okay, so in my mind, you have to write something. Like you can't just be like this, we're done. So you have to say a few words if you're trying to actually do an intermediate problem. And the few words are this. So we can say that since f of x equal to x squared minus 2 to the x is a continuous function, it is important that it's continuous, or really at least continuous on the interval that we care about. So I could be more specific and say, since f of x is continuous on the interval from -1 to 0, right, that's the only interval we're looking at right now, and f of 0 happens to be negative, and f of -1 happens to be positive. So we're going from a negative to a positive. Since it's continuous, it has to hit every value in between. Specifically, it has to hit 0. So then we get to say there must be a number between 0 and -1. There must be, we usually call it C. Such that f of C is equal to 0. Do we know what C is? No. Do we know approximately where it lives? Yeah, it's between -1 and 0. So somewhere between -1 and 0, this equation has another solution. And it's definitely not 2, and it's definitely not 4, because those numbers aren't between -1 and 0. So good. Yeah. Correct. It's not 0 or -1. Oh. I mean, I guess that would work. That seems really atypical to me, though. Yeah, I'm not familiar with that. Sure, I'm happy to look at it later, but yeah, that seems strange, but probably works. It's just different. I would never. Yeah, that's interesting. Okay, let's look at one more, and let's look at a different variety of it. So this is, in my opinion, the usual kind of intermediate value theorem question you will typically encounter in general. They're going to ask you to show something has a solution, and if they're nice, they'll give you the interval. If they're not nice, they won't. Nice is probably not the right word, but like, right? If they're trying to make it easier, they will give you the interval. If they're trying to make it harder, they will make you come up with the interval yourself. And if you have to come up with the interval, it's just testing points until you get one thing that's positive and one thing that's negative. And you should always, in my opinion, start with 0. So if no, I should also say here, right? I started with 0, and we got 0 minus 2 to the x was a negative. 0 minus 2 to the 0 was -1. And I know from experience, and you probably know as well, that 2 to the x eventually gets way, way bigger than x squared. So picking positive values is not going to be the right way to go, because this is just going to grow faster and faster. I'm going to have a smaller thing minus a bigger thing, which is going to be negative. So I should have known by looking at this that, oh, if I start at 0, going to the right is not going to help. I'm going to be getting more and more negative values. Instead, I should have automatically gone to the left, because I know to the left, this actually gets smaller and smaller and smaller, where this actually starts to get bigger. Because if you have negative numbers, more negative numbers squared get larger and larger and larger. So it's good to think about the sense of what kind of functions you have to look at when you do it. Well, let's look at another question here, which is a different variety of an intermediate value theorem question. It's more of a understanding question. So consider the piecewise function f of x equal to 2x minus 5, x is less than 2, and x squared minus 3 when x is bigger than or equal to 2. And observe, note that f of 1 is equal to negative 3, and f of 3 is equal to positive 6. So does there have to be a number c between 1 and 3 such that f of c is equal to 0? Why or why not? Well, if I was trying to answer this question, I first might just check to see, is there even such a thing? Like, is there a number between 1 and 3 where f of that number was equal to 0? Yeah. It's fair enough. So this says, does there have to be a number c between 1 and 3? You're welcome. Such that f of c. So let's try setting that thing's equal to 0 and seeing what we get. So if I set 2x minus 5 equal to 0, and I solve for x, I get 2x equal to 5, I get x equal to 5 halves. But the problem is 5 halves is not in the domain of that piece of the function. So it's not really a solution. Similarly, if I set the other thing equal to 0, I get x squared equal to 3. I get x equal to plus or minus the square root of 3. But both of those are also not in the domain of that piece of the function. Right? That piece of the function is defined when x is bigger than or equal to 2. There's no way x squared minus 3 is going to equal 0 if x is larger than 2. Because 2 squared minus 3 is 1, and any bigger value of x is going to give you a bigger output. So also not a solution. So at least it looks like there isn't a value c, right? So does there have to be? Well, we know there isn't, so I guess the answer is there doesn't have to be. But now the question really is, why doesn't there have to be? Because what are we, so really I should have asked, what's missing from the hypothesis of the intermediate value theorem that means we don't have to get all the values between negative 3 and positive 6? Right, is this function continuous? I don't know, is it? Let's check. So if we look at specifically 2, we know that f of 2 exists. I don't even want to bother finding f of 2, even though we could. But if we look at the limit specifically, the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left of 2x minus 5, which is 4 minus 5, which is negative 1. And the limit as x approaches 2 from the right of f of x is going to use the other piece, which is x squared minus 3, which is equal to 2 squared minus 3, which is positive 1. So not continuous, right? We've got this jump. Specifically, what's happening here is we have something that looks like 2x minus 5 on the left. So it does something like this. Right, you want to see the graph maybe? Yeah, you might want to see the graph. So there's the 2x minus 5 part left of 2. And here is the x squared minus 3 part to the right of 2. And so we definitely have the points f of 1 equal to -3 and f of 3 equal to +6. But because there is discontinuity, we are not guaranteed to get all the values in between -3 and +6. So because this function is discontinuous on the interval from 1 to 3, there is no guarantee of getting any specific y value between them. Between f of 1 equal to -3 and f of 3 equal to +6. So sometimes people ask questions about like more of an understanding of why is the intermediate value theorem working here or not working here. And it often has to do with the fact that the function may or may not be continuous. Not continuous, intermediate value theorem doesn't work. You can't say anything about it. Okay. Oh, I know what I want to say. There was something. Papers everywhere. So actually, let me ask you all. Let's talk a little bit more about limits to infinity, because I feel like we kind of skipped over that a little bit, and there's definitely a couple of questions that we haven't looked at that are, I think, worthwhile. So let me throw a couple of things at you, because I've seen these come up in people's classes. What if we wanted to look at the limit as x goes to infinity of square root of x squared plus 6x minus the square root of x squared plus 4x, which looks kind of awful. It looks like it's infinity minus infinity, which is an indeterminate form. So if you have infinity minus infinity, or infinity divided by infinity, or 0 divided by 0, or some other things we haven't talked about yet, if you have anything that is that sort of form, all that really means is you have to do more work. If you have something that's indeterminate, meaning we don't know what it is, it's our job to kind of figure out what it is. So we have to do work. And in this case, we're going to multiply by the conjugate. So we're going to write this as the limit as x goes to infinity of the square root of x squared plus 6x minus the square root of x squared plus 4x over 1, if you like, times the conjugate, the square root of x squared plus 6x plus the square root of x squared plus 4x over the same thing. And then we're going to multiply out the top. That's the whole reason for multiplying by the conjugate, so that the thing it's a conjugate of is actually going to simplify. The bottom is just going to stay as whatever we've got down there. So let's see what this works out to. Okay, so when you multiply these things together, you're going to get x squared plus 6x minus x squared plus 4x. I'm not even going to worry about the middle terms because we know they cancel out. All right, whenever you multiply by a conjugate, that's the whole reason for multiplying by the conjugate. The middle terms just go away. They subtract each other out. And then the bottom here is square root of x squared plus 6x plus the square root of x squared plus 4x. Okay, what can I do next? You can cancel those x squareds. X squared minus x squared, 0. 6x minus 4x, 2x. So left with the limit as x goes to infinity of 2x over the square root of x squared plus 6x plus the square root of x squared plus 4x. Okay, so here's what I would say about this. This isn't a rational function, right? It's not a polynomial over another polynomial, but it kind of has one of the same hallmarks as a rational function, which is that if we were trying to evaluate something like this, I might think about the highest degree in the top and the highest degree in the bottom. The highest degree in the top is 1, and the highest degree in the bottom although you can't really say degree because it's not the right word to use for the polynomial. But the highest degree in the bottom is kind of like 1, because it's kind of like the square root of x squared. Right? The highest power in the square root is certainly x squared, and then the square root of that is square root of x squared is kind of like x to the first. So I'm thinking I have a degree 1 over a degree 1. So I can probably do this sort of thing where I divide everything by x to the first. But before I can do that, there's something that we kind of have to deal with. This is where things get a little interesting. So I want to be able to divide by x. To be able to do that, I need to be able to pull out an x from those square roots. So I'm going to rewrite this in the following way. And this is kind of always the part that people, you kind of have to be shown this, I think, to really know what to do. Like if I had to do this problem, I'd never seen what to do before, I don't know if I would know. I had to have someone show me, be like, oh, okay, that's the way we're supposed to do this. So from this step here, in each square root, we're going to divide or factor out an x squared. So I have x squared times 1 plus 6 over x. And I have the square root of x squared times 1 plus 4 over x. And then we're going to write this as the limit as x goes to infinity of 2x over, how do I want to say this the right way? I'm just going to show the work. Square root of x squared times the square root of 1 plus 6 over x plus the square root of x squared times the square root of 1 plus 4 over x. And now here's the things. In this problem, we're not going to be dicey, but none of the problems can be dicey. The square root of x squared is the absolute value of x, not just x. Here it is, though, because x is positive. So here, since x is positive, because it's going to infinity, we can just say that this square root of x squared, which would be the absolute value of x, is just going to be x, because x is already a positive number. The absolute value of a positive number is just that number. So here we would write this as the limit as x goes to infinity of 2x divided by x times the square root of 1 plus 6 over x plus x times the square root of 1 plus 4 over x. And then you can either divide everything by x, or you could actually factor out an x from the denominator and then just cancel the x. It's the same work. I'm going to factor out because I don't know, it feels like less to write. So I have 2x over x times the square root of 1 plus 6 over x plus the square root of 1 plus 4 over x. And then I can divide these x's. X divided by x is 1. And finally, I can actually find the limit. This 6 over x goes to 0. This 4 over x goes to 0. So I'm left with 2 over 1 plus 1. So in this problem, it's kind of weird to say it, but in this problem, infinity minus infinity happened to be 1. This infinity was 1 bigger than that infinity. It's a dumb thing to say, but it's also kind of what's happening. This one's always just 1 ahead of that one. Get back to that over here. But they're both getting infinitely large. Let me say, let's see. Let's look at one more like this because I kind of want to show you the other thing that happens, which is that if you take the limit of something like this as you go to negative infinity, you have different results. Now, actually, so I should point out, because this actually, I've seen this in people's homework assignments. Actually, we could totally do that here. Yeah, it'll work. Never mind. So I should point out, sometimes people ask questions and they don't think they mean to, where someone might give you a question like this. I'm going to change it up a little bit to kind of show you. Someone might ask you, what's the limit? X goes to infinity. I'm going to make it a little bit different. Just kind of do what I want. Of x plus 2 minus the square root of x. I don't know what this answer is going to be really, but I don't really care. You could do the same sort of work. You can get something. It might be 0, it might be 1. But then people will also, as a follow-up, ask you this question. The limit as x goes to minus infinity of the square root of x plus 2 minus the square root of x plus 1. And the problem with this question here is you can't let x go to negative infinity, right? You can't be taking the square root of -7 plus 2 or -1,billion plus 2 or whatever. So this limit right off the bat, that doesn't exist. Because the x values we're approaching aren't in the domain of the expression. Cool. And I thought that was going to be a problem for this one, but it actually isn't. Because if you look at each of these things here, if you factor in x times x plus 6, or here x times x plus 4, if x is negatively infinitely large, you have a big negative number times another big negative number, which is a positive number. So your integral will still be positive and we're safe. Same deal here. So let's go ahead and look at the other side of this limit. Not that side way out there, but that side way out there. So I'm not going to write down all the work again because up to this point, the work is all the same. It's just if it's going to have a negative infinity instead of a positive infinity. So I'm going to start with this. The limit as x goes to minus infinity of the square root of x squared plus 6x minus the square root of x squared plus 4x. And I think it's valid for you as well. Like if you had to do this work, like not that anyone's mostly ever checking your work at this point, because it's a lot of web work kind of stuff. But if someone was checking your work for something like this, it would be totally valid to be like, oh, well, I've already done all the algebra once. I don't need to do all the algebra, the same algebra again. I think you should just jump to saying, oh, that's the limit as x goes to minus infinity of 2x over square root of x squared times the square root of 1 plus 6 over x plus the square root of x squared times the square root of 1 plus 4 over x. Perfectly legitimate. And then here's where things are more interesting. I'm going to rewrite this as the limit as x goes to minus infinity of 2x over the absolute value of x times the square root of 1 plus 6 over x plus the absolute value of x times the square root of 1 plus 4 over x. And here's where we have to remember that if x is negative, then the absolute value of x is equal to negative x. It always feels funny because you're saying the absolute value, it looks like you're saying the absolute value is a negative thing, and we know absolute values always give you positive things, but you're really saying the absolute value is positive. And if it helps to remind you, I remember here, let's replace x with a real number. Pick any negative number you like. And pick -8. If -8 is less than 0, okay, check, that works. Then the absolute value of -8 is -8. Oh yeah, that works. That's what we do when we have an absolute value. So that maybe helps you see how that's working. So when I write this, I really do have to write this is the limit as x goes to very negative number of 2x over negative x times the square root of 1 plus 6 over x plus negative x times the square root of 1 plus 4 over x. Question? And so then the work's the same as before. There's just a negative sign at the bottom. So if I factor out an x still from the bottom, I'm left with the limit as x goes to minus infinity of 2x over x times negative square root of 1 plus 6 over x minus square root of 1 plus 4 over x. X divided by x is 1. So then we take the limit, we get 2 over, that's going to go to 0, that's going to go to 0, and you've got -1 minus 1, which ends up giving you a -1. This is an example of a function that the limit to the right is +1, limit to the left is -1, or in other words, the limit to the right we have a horizontal asymptote that's +1, and on the left we have a different horizontal asymptote that's y equal to -1. Kind of neat. All right, that's all I've got. And I know it's a lot. That's all. That's it. I feel like I said a lot, but that is all. Good luck on your tests if you have them soon, or even if you don't, right? Good luck in general on your tests. Next week, I guess we'll try to move into talking more about the derivative stuff. So I think most of the classes are finally getting there to the limit definition of the derivative. So we will revisit that, talk about it more in depth. But as usual, if there are things that you need to see, want to see, like James, we talk about this, just let me know. I'm really happy to do whatever.
That's a good question.
Yeah.
So if we have like this function here,
Sure.
and you're trying to set it up with this formula,
Uh-huh.
would it be like this?
It's terrible,
Or
yes.
would it be like this?
No, it's definitely like this.
Like this?
Yep.
Okay.
This is, what that there is, it's not right, but that is this.
Oh,
And the problem with this is, I know it equals one,
I see.
and it's not gonna be what you want. The derivative is definitely not one.
Yeah. Dude, okay, I was hoping it was the other one.
No, so for that one, what you have to do is you have to take this and then you have to multiply this piece by x minus two over x minus two, and this piece by x plus x minus two over x.
To get this common denominator.
Yep.
Okay, and then you combine it and then,
And hopefully lots of stuff cancels at the top. It's not gonna be pretty.
yeah. Okay. Cool.
So
Thank you.
Mina,
Do you have practice midterms?
I believe I do. Let me check.
Are they on campus?
I think so. Now I'm not sure. Let's find out.
I think there are few on Grant website.
There are definitely some on Grant's website. But let's see if there's any on campus here. I do not have, I have practice finals on there, but I can find a practice midterm.
How do I get to grants?
So you can, there's actually a link in our Canvas, because I know Grant's website. If you just go to the top of the modules, second link, Grant's website. And then you have to click it again, because apparently I set this up in the terrible way. And if you scroll down to the bottom, there's midterm one practice problems and solutions, midterm two and solutions. That's a good place to start.
Are we going to cuts?
Yep.
And is Sarah coming?
Let's see. I don't know. Let's see. I know her. I think she's there right now,
Oh,
but she might not be because there's another like staff event going on today that she's probably attending. So normally on Tuesdays and Thursdays, I believe she'd be there right now, but I don't think she is today because I believe she is doing something. But let's see. Sarah is in CADS Monday from 10 to 15 to 11:15, Tuesday, Thursday from 11:30 to 12:30, and then tomorrow from 2 to 3.
thank you.
You're welcome. What's up?
That was his homework assignment last week.
Sorry, what am I looking at exactly?
So this homework problem,
Uh-huh.
yeah. So I'm not sure how to do it,
Which one?
all three.
Great. I would be happy to talk to you about
Yeah.
that. Not right now.
Sure.
But if you like if you, so in general, like if we're in class and you have a question like that, I might not do it exactly, but I can certainly do a problem similar to it. So if you say something in class or even before class, like shoot me an email, whatever, I'm happy to like look at things like that. I do have office hours today from 3 to 4 in CADS, which is the Center for African Diaspora Student Success. I'm happy to look at it though.
Sure.
That,
Did you just like plug in zero? Is
I
that
didn't plug in zero.
or the negative infinity?
I mean, I wouldn't say I plugged in, but essentially I plugged in. I said, oh yeah, if X is getting very, 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 very negatively large, 6 divided by a very large number is a very small number.
Okay.
So it's going to 0. That's going to 0.
All right.
Sure.
We found one of the solutions that we could change